today we're going to talk about summations. Let's suppose you wanted to add up all the integers from 1 to 100. So 1 plus 2 plus 3 plus 4 all the way up plus 99, 100. You can see that this is going to take a little time, right? 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, so on and so forth. But what you might be able to do is pair these numbers together. And notice that if you take the last two numbers, 1 plus 100 and 2 plus 99 and 3 plus 98, you're getting 101 and 101 and 101 and all the way up here, 50 plus 51 is 101. And you'll notice that pattern that you have 50 pairs of 101, and so then maybe you would see that it would sum up to 5,050 a little bit quicker. We can write this as a summation where we're summing these numbers 1, 2, 3 all the way up to 100, starting at 1, ending at 100, and just itself, so we'll call that I. So then this would represent the summation of 1 plus 2, so on and so forth. Okay, so how does that help us? Well, we have some properties of summations, which are really nice. So if C is a constant, if you are taking the summation from 1 to n of C times something, you can actually pull that C out. And another, we have this kind of sum and difference rule that says if you're taking the sum from 1 to n of two terms being added or subtracted, you can take the sum of the first term plus or minus the sum of that second term. And so those are really nice properties. And then we have some summation formulas. So the first one is that the sum from 1 to n of 1 is n. So if you wanted to add 1 n times, 1 plus 1 n times, you would get n. Here's a summation formula from 1 to n of just I. This is very similar to that first example we did. If you wanted to add 1 plus 2 plus 3 all the way up to 100, you take this ending term n times n plus 1 all over 2. The summation from 1 to n of I squared is this ending term here, n times n plus 1 times 2n plus 1 all over 6. And if you wanted to take the summation from 1 to n of I cubed, it would be n times n plus 1 all over 2, but this entire quantity squared. So let's revisit that example, adding 1 plus 2 plus 3 all the way up to 100. This matches one of those formulas we had just talked about here, where our ending term is 100. So the sum from 1 to 100 of I would be 100 times 101 divided by 2, which gives us that answer 50/50. Let's look at a few other examples. If we wanted to take 4 plus 9 plus 14 plus 19 plus 24 plus 29 all the way up to 59, that can be written as a summation from I equals 1 to 12 of 5I minus 1, right? 5 times 1 is 5 minus 1 gives me that first term 4. Plug in 2, 5 times 2 is 10 minus 1 gives me that second term 9, so on and so forth. 12, 5 times 12 is 60 minus 1 gives me that last term of 59. Now you can pull out your calculator and you can do 4 plus 9 plus 14 plus 19 all the way up to 59 and see what happens. Or we can look at this summation right here. And we can break this up using our summation properties. This coefficient can come out front, and the sum and difference rule says I can take the summation of the first one minus the summation of the second one. Now look back at your notes from a couple minutes ago. This matches a formula, and this matches a formula. And so we get this 5 carries through. The sum from 1 to 12 of I would be 12 times 12 plus 1 all over 2, minus the sum from 1 to 12 of 1 would just be 12. And when you calculate that out, you get 378. I encourage you, since it's not that many terms, to take 4 plus 9 plus 14 plus 19 plus 24 plus 29 all the way up to 59 and see that you get the same answer. Let's look at another one. 1 plus 6 plus 13 all the way up to plus 222. This can be written as the sum from 2 to 15 of I squared minus 3, right? 2 squared minus 3 gives me 1. 3 squared is 9 minus 3 gives me 6. 15 squared is 225 minus 3 gives me that 222. Now, I want you to notice something. Here, the sum is starting at 2. But if you look back at our summation formulas, they all started at 1. So what we can do is we can actually rewrite this as the sum from 1 to 15, but then we just take away that additional term from when I is 1. So when I is 1, we get 1 squared minus 3, so we'll just take that term away at the end. Here we can break this up into two different summations being subtracted. So we have the sum from 1 to 15 of I squared minus 3 times the sum from 1 to 15 of 1, and then we're going to subtract off this negative 2 at the end. This I squared matches a formula, and this 1 matches a formula. So when we plug those into our formulas, we get 15 times 16 times 31 all over 6, minus this 3 carries through. The sum from 1 to 15 of 1 is just 15. And then minus that negative 2 at the end. To get rid of that additional term, we added by turning this I into a 1 when we were supposed to start it at 2. When we calculate this out, we get 1240 minus 45 plus 2, and that ends up being 1197. And again, I encourage you to take your calculator and actually sum these numbers. You know, do 2 squared minus 3 plus 3 squared minus 3 plus 4 squared minus 3 plus 5 squared minus 3 all the way up to 15 squared minus 3, and you'll see we get the same number of 1197. You'll notice very quickly that these summation formulas, especially if we were going from like 2 to 100, would be a lot quicker than actually calculating all of those numbers up and adding them. I want to look at one more example. I want to introduce a limit to you. So let's take the limit as n is approaching infinity of 1 over n to the 4th times the summation from j equals 1 to n of j cubed. This right here is a summation formula, except instead of calling it I, I'm calling it j. So right here, it's this formula n, that ending term n times n minus 1 all over 2 quantity squared. So now let's take a look at this limit. The first thing I'm going to do is I'm going to distribute this square, right? I'm going to take the n squared, the n plus 1 squared, and the 2 squared. I will actually square this n plus 1 squared, so that's n plus 1 times n plus 1, and that gives me n squared plus 2n plus 1, and that 2 squared gives me 4. And so now I'm going to distribute that n squared, and we have n to the 4th, 2n cubed, n squared, and then that n to the 4th times 4 gives me 4n to the 4th. Now, look at this for a little bit. We have a limit at infinity, as n is approaching infinity of this term right here. We had a little trick that we talked about. We could take the highest power of n in the bottom and divide everybody by that, and then reduce, right? So we're going to do the n to the 4th over n to the 4th, this over n to the 4th, over n to the 4th, and over n to the 4th, and reduce. And we get the limit as n approaches infinity of 1 plus 2 over n plus 1 over n squared all over 4. Now we're ready to take that limit. As n approaches infinity, 1 will go to 1. As n approaches infinity, 2 divided by n will go to 0. 1 over n squared will go to 0. And 4 will stay as 4. And it turns out that this limit is 1/4. That's it for summations. We'll see you next time.